first FPGA seminar of 2015-2016. And we'll start off with Andrew Bitar and his talk on work on networking, building networking applications from an NoC-Enhanced FPGA. Thanks, Vaughn.
Hello, everyone. The slides may get fuzzy at times. We've been trying to fix that, but hopefully you can read the slides anyways. Today I'll be presenting some of the work I've been doing towards the completion of my master's degree here at U of T. My work builds upon prior work that proposed embedding a network-on-chip on FPGA devices. And what we propose is to build applications from this device as well as tools that enable these applications. I'll begin with some background and motivation. FPGAs today are highly heterogeneous devices. Over the years, they've been enhanced with hard blocks such as DSPs, transceivers, and hard SRAM blocks with the aim of increasing the logic, memory, and I/O capacity of the device. However, the soft interconnect of FPGA devices has remained relatively the same. It still consists of single-bit connections made up of wire segments etched together with multiplexers, and for most designs running at around 100 to 400 megahertz. Now, this can become a bottleneck in many designs, especially with the increasing amount of I/O bandwidth being brought on chip. Here we see, from generation to generation, Altera Strax devices have increased the amount of transceiver bandwidth being available, largely in response to the demands of the communication and networking industries that form about 45% of the FPGA market. Now, on this chart, we see the three models of each generation with the highest transceiver bandwidth made available. And we see from Strax 1 to the upcoming Strax 10, the amount of transceiver bandwidth that's increased has been about 30x. And there have been some experts that have pointed out that this is actually a greater increase than Moore's Law. Now, given that we're bringing all this bandwidth onto the device, can we actually bring this bandwidth across the chip? As we mentioned previously, most FPGA designs run around 100 to 400 megahertz. So if we consider an example where the transceiver is bringing 2 terabits per second of data onto the chip, and you're using a design that's running at 200 megahertz, you must use very wide data paths, in this case 10 kilobit wide data paths. Now, not only does this pose a difficult time enclosure problem for designers, it also consumes a lot of the FPGA resources. So what we argue is that FPGAs are in need of a new system-level interconnect that raises the level of abstraction and makes it simpler for designers to close timing on these designs. Now, some of you may already be familiar with some of the work done by our group led by Mohammed, where we proposed such a system-level interconnect in the form of an embedded network on chip. This network on chip consists of routers and links that have been hardened into the FPGA's fabric, and the design that we've proposed is a 16-node mesh with routers equally spaced across the FPGA's fabric. The proposed NoC also uses a flexible fabric port that performs clock and width conversion between the compute modules that are built out of the soft fabric and the hardened NoC. The NoC that we propose is a 16-node mesh with 15-bit wide links, and the cost of this mesh is about 1.3% of the core area of a large Stratix 5 device. Prior work has made many compelling arguments for building the case for the network on chip embedded on the FPGA. One, for example, we've shown that it is considerably smaller, faster, and more power efficient compared to an equivalent soft NoC. And since this hardened NoC runs at about 4 times the frequency of the FPGA fabric, it is much more effective at transporting high bandwidth coming from the transceivers across the chip. Additionally, through the flexible fabric port that can convert the clock frequency in a flexible way, the NoC can actually act as a decoupling mechanism for compute modules, allowing them to run at their own frequencies. Now, despite all these compelling arguments, FPGA vendors remain unconvinced. They say that despite the fact that this NoC that we propose only consumes 1.3% of the FPGA fabric, that 1.3% is still considered quite precious. In order to justify the cost of including this mesh, they need to see real compelling and concrete applications that can benefit from its inclusion and that will drive up the sales of future FPGA devices. They also need to see the appropriate CAD tools developed that will allow designers to take advantage of the benefits provided by this embedded NoC and allow the easy porting of designs previously created for older FPGA devices to this new FPGA device. So the work that I set out on for my research has focused on addressing these concerns. So for the remainder of my presentation, I will first begin by presenting some of the tools that we've created in order to build these applications on these new devices, as well as 2 application case studies. And we'll start with a discussion on the tools that we've created. Now, since an embedded NoC does not yet exist on FPGA devices, we needed a way to simulate its existence in our design. A widely used NoC simulator is Booksim. It is comprehensive, cycle accurate, and it allows for the customization of various interconnection network parameters. This includes the topology, routing algorithm, and flow control mechanism of the NoC. Now, one limitation of Booksim is it does not actually simulate the contents of the packets that it's simulating. It only takes the size, source, and destination of the packets in order to simulate their traversal through the network, as well as measure its latency. So in order to use Booksim, you simply feed it a configuration file that configures the NoC parameters, and it simulates the NoC that you desire. Now, what we wanted to do is we wanted to create our own designs in HDL, as any other FPGA designers were, but create compute modules that use the network that's been simulated in Booksim in order to communicate. So what we created is a tool called RTL to Booksim. This tool acts as an interface between the network that's simulated by Booksim and our compute modules that we wrote, and our RTL that we wrote. So if we look at a high level, let's say we have a compute module 1 wanting to send data compute module 2 through the simulated NoC. It would forward the packet to RTL to Booksim, which would pass the packet onto the network that's simulated by Booksim. Booksim would simulate its traversal to the NoC before giving the packet back to RTL to Booksim, which would then forward the packet onto the module that it's destined for. Now let's take a quick look under the hood of RTL to Booksim. We see that this interface actually consists of 2 interfaces. The first is the RTL interface, which actually connects the compute modules that we've written. This interface uses System Verilog DPI in order to communicate with the software simulated network that's been simulated in Booksim. So the RTL interface passes the packet onto a Booksim interface that then uses Unix socket communication in order to feed the traffic and receive traffic from Booksim. Now, as I mentioned to you earlier, Booksim cannot actually simulate the contents of the packet. So what we did is within our RTL interface, we locally stored the contents of the packet while its traversal is simulated in the network. So here, a packet's data is held in RTL interface while the packet's traversal is simulated, then it's rejoined with the data before being sent to the compute module that it's destined for. This simulation tool allows us to simulate designs that use the embedded NoC as our communication architecture. The simulator that we built has a very easy to use interface. In order to use it, you would simply instantiate an NoC module in your HDL that has parameters where you can set the various NoC parameters, as well as the interface for each of the routers in the network. So for example, if we wanted to connect a compute module to router 5, we would use the router interface to connect our compute module to the network. Now, simulation is just one of the steps to our design process. Another key step is the synthesis, place, and route. This step will allow us to answer the following questions. Specifically, when connecting to these routers that have been embedded in the FPGA, does this create interconnect choke points within the fabric? And do these choke points then consequently have a negative impact on the critical path delay or even this feasibility of synthesizing our design on the fabric? And this also will allow us to figure out how many FPGA resources consumed, which will allow us to assess the efficiency or the overall hardware efficiency of our design. Now, in order to emulate the existence of this embedded NoC in an FPGA, we use Quartus partitions to emulate their existence. Each of these partitions have the same size, location, and connectivity of the embedded routers that we proposed. So in our RTL, we connected these partitions, and the place and route engine uses these connections in order to place compute modules near the routers that they're connected to, as you can see in the example here. Now that we've gone through the tools that we've developed that allow us to develop applications that use this new FPGA device, we'll move on to some of the case studies that we've built. The first is the network switch. The network switch is a fundamental building block in communication and network infrastructures. It's used in data centers as well as wide area networks and local area networks to switch data from their sources to their destinations. At a high level, a switch contains the following components. It has input ports and output ports that are interconnected using a full crossbar that brings data from input to any output. For handling scenarios of contention, such as when you have multiple inputs sending to a single output, we have buffering at our input ports and our output ports. Excuse me. So the buffering allows these scenarios of contention to be handled with the addition of scheduling logic that actually allocates the buffering and crossbar when contention occurs. In order to build such a switch on an FPGA device, we first need to bring the data onto the chip. And we do that through the transceivers that we've seen have enough bandwidth to support the network demands that we see today. However, it still remains questionable whether we can actually switch this data on the soft reconfigurable fabric of the FPGA. So we looked into prior work to see what has been done in terms of switch fabric design on the latest FPGA devices, and we saw that very little work is actually out there. And this comes as no surprise, given that the very nature of a switch design requires many multiplexers in order to perform the switching, as well as long and wide data paths to bring the data from the transceiver to the multiplexers and back to the transceiver. Now recently, there has been a fairly clever design that has proposed leveraging the hardened resources already available in the FPGA in order to perform some of the switching function. This was work published in 2012 in the FPGA conference, where Dai Zhu showed that you could build a switch that has relative efficiency by using the hardened SRAM cells on the FPGA to perform some of the switching. And since these hardened SRAMs are built out of ASIC technology, they can actually run at a higher frequency and therefore perform switching at a more efficiently than if you were to build it out of the reconfigurable FPGA fabric. The design that they proposed achieves 10 gigabits per second per port switching for a 16 by 16 switch. Now what we propose is to extend this concept of leveraging a hard block on the FPGA to our NoC-Enhanced FPGA. In our design, the NoC is the crossbar. So for a 16 by 16 switch that's equivalent to the one that Dai and Zhu proposed, we would connect each of the 16 transceivers to its own unique router in the mesh that we proposed. Now note here that we're building a switch out of the NoC that was originally proposed by Abdel Fattah and Betz, where they proposed this NoC without any mind of what type of applications necessarily would use the NoC, simply that they wanted a general purpose network to be available. So here we're taking the same parameters and building a switch out of it. So let's see how this would work. A packet would arrive at a transceiver. The transceiver performs serial data recovery before bringing the packet onto the FPGA's fabric. At the FPGA's fabric, the designer can choose to do an optional amount of processing and buffering before bringing the packet to the hardened NoC. At the NoC, the fabric port performs clock and width conversion to bring the packet onto the NoC, and the NoC's routers then steer the packet across the chip to the router that is connected to the transceiver that the packet is destined for. The fabric port then performs the opposite conversion, bringing the packet back to the FPGA fabric, where the designer can optionally choose to do more buffering and packet processing before bringing the packet back out of the transceiver. All this was done while leveraging the efficiency of the NoC along with the reconfigurability of the FPGA. So this allows the design to have some degree of flexibility that's very suitable for the demand of programmability that computer networks currently have. And we'll talk about that further in the next application that I will show. Now, the NoC that was proposed already contains buffering within it. And given that we know that a switch requires buffers in order to handle scenarios of contention, we want to see if that buffering that's already available in the routers of the NoC is sufficient for our switch. So let's consider the classic contention scenario where we have two different input ports. Here we have input 0 and input 3 sending data to output port 9. Under this scenario, the packets meet at the router that is connected to output port 9, where they're both asking for access to the output port. So this is a scenario of contention where only one packet can be granted access to the output port while the other must be buffered within the router. Now let's say this scenario happens continuously over a long burst of traffic. Eventually the buffer at the router will become full, causing contention to be back pressured to downstream routers. Eventually, if the burst continues, those buffers will become full, causing more and more contention that will eventually make its way back to the input ports. This will prevent, if this scenario continues, this would prevent the input ports from actually injecting any more data. And additionally, because input-output paths within the NoC crossbar are shared, other paths can also be blocked. So here, for example, the path between node 3, or let's say node 2, and node 11 also uses this router, which is blocked because of the contention that happened from input port 0 and input port 3. So here we see that this scenario not only prevents nodes 0 and 3 from injecting, but can also create contention at other ports as well. So in order to alleviate this contention, what we did was we introduced output buffers in our switch. The output buffers hold the packet outside of the NoC crossbar, alleviating the contention within it, and thereby not blocking any other paths within the switch. Now, we have output buffering and we also have buffering within the routers. Is that enough for our switch to perform the efficient switching function? Well, let's consider another scenario of contention. Here we have two inputs sending to their own two outputs. Here we have input 0 sending to output 5 and input 3 sending to output 6. Under this scenario, the inputs are sending to two different outputs, but because the paths within the crossbar overlap, contention can still occur. So here we have more contention. This contention cannot be alleviated by output buffers because the contention happens away from the router that's connected to the output buffer. So if this contention continues to happen, the routers will become full, eventually making their way back to the input ports that we saw previously. So in order to prevent any packets from being dropped at the input port, we need to introduce input buffers that act as a safety net here. They will hold packets if this type of contention continues and makes its way back to the input ports. So overall, our design has buffering at the inputs, the outputs, and the ones that have already been built in the routers. We call this type of buffering combined input, crosspoint, and output queued switch. This is a new type of switch that, when used in combination with our NoC crossbar, can have very nice properties, which we will now evaluate. Let's begin with evaluating throughput. The NoC that was proposed has 150-bit wide links running at 1.2 gigahertz, so that gives each link a bandwidth capacity of 180 gigabits per second. Now, some of that bandwidth is used to transport control information, so that leaves about 150 gigabits per second left for data. Now, in order to determine what type of throughput our switch can handle, we need to consider what is the worst-case traffic pattern that the crossbar must support. And this is illustrated in the figure on the left here. So we can see that under this worst-case traffic pattern, a single link must handle 3 times R, where R is the injection rate of one port. Now, given that this is the most load that a single link can handle, and a link can support up to 150 gigabits per second of data bandwidth, that, using some basic math, we can figure out that each port, our switch can support about 50 gigabits per second at each port. And for a 16 by 16 switch, that is approximately 820 gigabits per second of aggregate bandwidth. We used our RTL Booksim simulator in order to measure the latency of our switch, and we compared it to the latency reported by Dai and Zhu's memory-based switch. We first assessed a 16 by 16 10G switch that is equivalent in terms of specifications to the one that Dai and Zhu proposed, and we saw that our latency overall is better under all injection rates. And here under this plot, we see latency as a function of injection rate, where injection rate is the fraction of cycles that a packet is injected into the switch. So for example, a 0.6 injection rate, we have 60% of the cycles during the simulation a packet is being injected. And this is a common way of assessing latency in switch designs across the industry. So we see that our switch achieves about half the latency of the Dai-Su switch and also saturates at a later injection rate, indicating that it can handle more bursty traffic scenarios. Now, in the previous slide, I showed that our switch can actually handle up to 50 gigabits per second per port. So we also simulated our design at 25G and 40G, which are common Ethernet standards used today, and we see that the latency remains quite good. We used our synthesis in place, or our CAD engine, or CAD flow, I should say, to assess the hardware cost of our design and compared it to the one reported by Dai and Zhu. Overall, we found that our switch is 1.8 times more hardware efficient compared to the memory-based switch. Now we also wanted to assess whether our design provides any form of power efficiencies. Now Dianzu's work doesn't actually report any power numbers. So what we did was we used Xilinx's power estimator along with the resource utilization numbers provided by Dianzu in order to estimate the power consumption of their design. We used the same methodology to assess our power in order to provide a fair comparison, and overall we found that our switch is approximately 1.6 times more power efficient compared to Dianzu's previously reported memory-based switch. So to summarize, our switch can handle 820 gigabits per second of aggregate bandwidth, which is the most bandwidth of any previously reported FPGA-based switch design. It also achieves about 2x latency savings compared to Dianzu's memory-based switch, as well as being 1.8 times more hardware efficient and 1.6 times more power efficient. Now before this design, I should note that Dianzu's memory-based switch was the most efficient and handled the most throughput of any FPGA-based switch design. And you can see here that with just the introduction of this embedded NoC proposed by Bitar and Betz, we can achieve a significantly better switch design. Now that we built this switch, so what? Is that all we can build out of our NoC-Enhanced FPGA? Well, not at all. The NoC that we've introduced to the device was meant to service a wide array of applications on the FPGA. We could build today this switch that we just proposed, and tomorrow an entirely different switch that supports different radix or different throughput, or a completely different application. The point is that the embedded NoC allows for efficient switching while sacrificing minimal reconfigurability on the FPGA. And I will illustrate this point by moving on to our next application, not switching, the packet processor. So let's begin by defining what a packet processor is. In most general terms, it is any form of hardware that performs actions based on the contents of received packetized data. So a packet that may arrive at a packet processor may have a combination of different headers. Each header has its own protocol that must be processed. So for example, we see here an example packet that has an Ethernet header for layer 2, an IPv4 header at layer 3, and TCP header at layer 4. Now the various different combinations of protocols received by a packet processor and the packet's headers can be represented by a packet parse graph. The packet parse graph contains all the different combinations of protocols that may be received in one packet by a packet processor. So if you follow all the paths, you can follow any path within the graph and form a packet that the packet processor must support. So a packet processor is essentially spec'd by the parse graph that it can actually process. So for example, here we had an Ethernet IPv4 TCP header. You could have another packet for this parse graph that is an Ethernet, VLAN, IPv6, and TCP header. And you can use any path within this graph to form a new combination of packet. Now, a programmable packet processor, on the other hand, can actually modify this parse graph on the fly. It can modify the edges or introduce new nodes in order to support network evolution. Now, this network evolution has become a hot topic in the networking industry. With new protocols coming out at a rapid rate, networking infrastructures now have an increased demand for programmability within their networks. Since the network is evolving at a rapid rate, these network infrastructures don't want to go through frequent, expensive hardware replacements. So if you build programmability in their hardware, you don't need to do that, and you save cost and time as well in terms of updating your infrastructures. And the popularity has been illustrated by the emergence of software-defined networking and the standard of OpenFlow, which has been quite popular in the academic community. OpenFlow specifies a standard for interfacing a control plane that programs a fixed hardware data plane built largely out of ASIC-based hardware that can still be configured to update their protocols that they can process. So let's take a closer look at the OpenFlow standard and what they specify for their packet processor architecture. OpenFlow specifies that their packet processor should be constructed out of a cascade of match action flow tables. Each of these flow tables contains several entries, and a culmination of these entries forms a processing rule. Each of these match action entries contain a field that need to be matched against from within a packet and a corresponding action to be taken. So for example, one field may have a match for the ether type and MAC source address within an Ethernet header, and the corresponding action may be to drop a packet. So let's say a packet arrives at this table, and its field for ether type and MAC source address match this entry within this flow table, then the packet processor will perform the action of dropping the packet. In order to modify the parse graph that such a packet processor can support, you simply need to modify the entries within the flow tables. So let's take a look at an example of a potential packet processor, or an OpenFlow packet processor architecture. Here we see the beginning of the pipeline of flow tables with the first two flow tables shown here. Suppose a packet were to arrive at the first flow table. The processor has been programmed to first begin by matching the ether type within the Ethernet header. Under this scenario, the packet is matched against the first flow table with the IPv4 entry. In this entry, the packet processor has been programmed such that if this entry is matched, the corresponding action is to actually identify where's the location of the IP source address in the next protocol header. So using this information, the packet moves on to the next flow table, where it can now locate the IP source address within the IPv4 header and match now against the second flow table. Given this match, the corresponding action for this case, let's say, would be to decrement the time to live field in the IPv4 header. So the packet then, or the time to live field is first located within the packet and is updated correspondingly. So how exactly would you perform updates to this packet processor in order to introduce new protocols or update the flows that are supported within its architecture? Well, let's take a look at an example. Let's take a closer look at flow table 2. Let's say we want to update a match field in order to support, let's say, a different address to be matched against. You would simply need to update one of the fields within the table. If you wanted to introduce more entries, you could also do the same, where you would add new fields for new addresses that you want to match against. Now I'm going to bring up a slight limitation to this architecture. We see in this example that this flow table is currently full. All of its entries have been consumed by a different IP address, or a different combination and match field. It doesn't have to be an IP address. It could be a different field that you match against. Let's say, given the demands of a certain packet processor and the network, it asks for even more entries, and we want to write another entry. Well, we can't under this scenario because the table that has been fabricated in this chip cannot support any more entries than the ones that it already contains. So either we need to replace an entry that's already there, or do expensive hardware replacement in order to introduce a new OpenFlow pipeline that has tables that are bigger. Additionally, let's say we are introducing a new protocol that has fields that we want to match that are wider than the table that has been built in this architecture. So one example is, let's say originally this table was built to support IPv4 address matching. IPv4 addresses are 32 bits wide, so the table was constructed to fit that address. But let's say at a later point in time, IPv6 were to be introduced. IPv6 addresses are 128 bits wide, and so such a field would not be able to fit in one match table entry. This is illustrating the limitations of OpenFlow when it comes to building programmability in packet processors. Although OpenFlow introduces some flexibility, it is still limited by the fact that we're using ASIC technology to build this architecture. The table widths, depths, the number of tables, and even action set are fixed upon chip fabrication. So say we need new protocols that need different actions or different tables that are not built into the architecture, expensive hardware replacements are still needed. So of course, one possible solution would be to build this architecture in an FPGA. An FPGA is inherently reconfigurable, so you can reconfigure the size of the table or the action set in order to support new protocols as they come out. And this was actually done in previous work in Tig and Brebner's PP design, where they actually built a very similar match action or cascade of match action tables in order to perform packet processing. Now what we argue is that the OpenFlow standard was built to target or to introduce programmability into ASIC-based packet processors, whereas FPGAs are already inherently reconfigurable. So instead of using the OpenFlow standard to build a packet processor on an FPGA, what we're proposing is to leverage the FPGA's already reprogrammability in order to build an even more efficient design. And we do so using our proposed architecture, which we call the module-based packet processor. In this design, we use a combination of processing modules, where each processing module is dedicated to processing a single protocol. A packet arriving at this packet processor would be switched between the different processing modules corresponding to the protocols that are contained within its header. Crossbars are used to switch between the modules, as are seen in the figure below. You can perform updates to this packet processor by updating the individual processing modules or introducing new ones. So for example, let's look at the packet parse graph that we showed earlier and how it would look in this architecture. We see here that each processing module is dedicated to a single protocol to be processed. We've performed processing module duplication in order to increase the processing bandwidth for that individual protocol. So here we have 4 of these Ethernet processing modules, so we can support 4 times the processing bandwidth of a single line. So suppose 2 packets arrive at this packet processor, one with an Ethernet IPv4 and TCP header, and the other with an Ethernet IP6 and TCP header. The packet would first be processed by the Ethernet processing module, which would perform Ethernet processing and determine the protocol of the next level header. So for the first packet, it's determined that the protocol is IPv4, the second is determined as IP6. Using this information, it forwards the packet to the processing module that corresponds to that protocol. So here the first packet is sent to an IP4 module and the second is sent to an IP6. They next determine that the next protocol is TCP, so they are sent to a TCP module before being forwarded out of the packet processor. Now, this seems nice, but as we illustrated earlier in our switch application, full crossbars synthesize quite poorly in FPGA designs. And that is the caveat here. If we were to build these full crossbars out of the soft reconfigurable fabric, it would be quite inefficient. So I bet you can guess what's coming next. We use the hard NoC as the full crossbar in the switch design, and we call it the NoC packet processor. Here, as we illustrated in our switch design, the NoC can perform efficient switching between the processing modules in order to process packets. Now, one cool feature about this design is that we also are using the embedded NoC, which, as I described previously, performs a decoupling effect between compute modules. So we can actually update compute modules on their own through partial reconfiguration in order to perform processing module updates. So let's look at an example here. We built our design an Ethernet IP4, IP6 TCP processor out of our design. And here you see we have our 4 Ethernet processing modules, 4 IP4, IP6, and TCP modules. And each line is running at 100 G. So overall, the bandwidth that we support in this processing module is 400 G of packet processing. And we can go through how a packet can traverse such a NoC. It's quite simple again. Goes through the Ethernet processing, then is sent to the layer 3 protocol that corresponds to its packet, and finally to the TCP module before being sent out. Very simple, but here we have a NoC that efficiently manages to switch between the processing modules. Now, let's illustrate how we would perform rule updates in our NoC-PP design. One way would be to use actual tables within our processing modules and update these tables as OpenFlow does. But of course, we want to be able to reconfigure these tables in order to support new widths, depths, and maybe new actions available. So what we can do is use our design to perform partial reconfiguration to update designs as new protocols come out. So here we've added another IPv6 module because let's say we want more processing bandwidth for IPv6, and we've introduced UDP to the design. And we can do this through partial reconfiguration because the NoC acts as a decoupling mechanism for modules, having each module capable of running at their own clock frequency separated from the rest of the modules in the design. Now we showed that our design can support 400G by duplicating each of the modules 4 times, but given that we have more room in our FPGA fabric, we can duplicate our modules even more, supporting even higher bandwidths. And we actually built our design for 800G processing by duplicating each of the modules 8 times. We compared our 400G packet processor with the equivalent 400G processor built in the PP design by Tegan Brebner for 2 different applications. So just as a reminder, the PP design used a similar OpenFlow architecture built in an FPGA. We simulated and synthesized it for an application that simply used Ethernet, that simply did Ethernet processing, and another that did full Ethernet, TCP, IP4, and IP6 processing. And what we found was our design is both more efficient and achieves latency savings compared for both applications. Now what's interesting here is the degree of savings of our design is higher for smaller applications than larger ones. And the reason for this is our design uses what is known as a use only what you need design policy. For the simple Ethernet design, our design simply needs to instantiate Ethernet modules. That's all it needs. It does not need to instantiate any other processing modules. It can instantiate them later if those protocols are needed. However, for the PP design, their match action tables come with a lot of overhead in introducing these tables and having the action set available. So given that their design has a lot more overhead, for smaller designs, our NoC-PP design achieves significant efficiencies because it doesn't have this overhead. Now you may wonder what would happen if we built our module-based packet processor out of the traditional FPGA fabric. Would we still achieve savings? Well, in this chart here, we did so. We assessed our design using a soft NoC rather than a hard NoC. And then we also built a customized soft crossbar that targets specifically the packet processor that we built. And what we found is, despite the fact that our processing modules are quite cheap, interconnecting these processing modules out of the FPGA fabric is prohibitively expensive. Especially the soft NoC that contains all the features of the hard NoC is quite expensive to synthesize on the FPGA. And even if we tailor a crossbar that's specific for a packet processor, it is still quite expensive because we need these wide data paths in order to support the high bandwidth of the packet processor. So overall, we find that our NoC-PP design only manages to achieve design wins when it combines the efficiencies of the hard NoC with the efficiencies of our module-based packet processor architecture. Let's go through a quick recap of what I've talked about today. So we began with talking about the current state of the case of the NoC-Enhanced FPGA and saw that FPGA vendors want to see more applications and tools to justify its inclusion. So we set out on introducing these tools. We introduced RTL to Booksim, a mechanism to simulate a design using an embedded NoC, as well as introduced partitions in Quartus in order to emulate the existence of routers on the FPGA's floor plan. We went through 2 application case studies and saw that both achieved very good efficiencies compared to previously proposed designs on FPGAs. If you'd like to learn more or read more into the work that we've done for the work that I presented today, I refer you to some of our published works. This work was highly collaborative and could not have been done without the help of many different individuals that you see here, all out of the University of Toronto. So to leave you with some final thoughts, with the increased demand for programmability in network infrastructures, FPGAs are well poised to take advantage of this because of their inherent reprogrammability. However, they still need a tweak in order to be able to handle the high bandwidth demands of computer networks. We argue that the addition of an embedded network on chip can give FPGAs this on-chip bandwidth while maintaining its reprogrammability. The network switch and packet processor that I've discussed here are just 2 of many potential motivating applications that can benefit from the inclusion of this hardened NoC on the FPGA. And I encourage anyone who's looking for a new project to set on for their research to look into maybe new applications that could benefit from this architecture. Thank you.
Okay, great. So, questions? It was such a great talk. So clear.
So the applications that you've built, you have to basically do the placement of your design, or at least the choice of which network switch to connect to. You're doing that, like the designer is doing that manually?
Right. So in the applications that I've built, I basically chose which router each compute module is connected to. Now ideally we would have as we do our work and build more tools for this architecture, we would have tools that can intelligently select which router to connect to in your design based on some form of parameters that you feed it. But for our work, that doesn't exist, so I went through and I actually messed around with different combinations of router compute module connections and saw which one achieved the best latency or throughput.
How did you come up with the estimate that, or maybe that's not you, but the 1.3% overhead?
Yeah, that was actually previous work done by Mohammed. They proposed a 16-node mesh with 150-bit wide links and went through the process of like going through cadence and figuring out how much it costs, and using the overall area of the ASIC NoC, compared it to the core area of the FPGA, and then determined that it was about 1.3%.
Are these NoCs fairly uniformly distributed on the FPGA?
Yeah, so the one that we're proposing actually has routers equally spaced across the FPGA.
Is that realistic? Like, does that interfere with other things that you might want to use the FPGA for?
So do you mean, would it replace resources that you would want at those locations?
Or interfere with the routing between resources for other kinds of designs?
So my understanding is it would need to replace, well, whatever layer it's synthesized on, it would need to replace the metal for the wires that it needs to connect the routers. But my understanding is, and I'm not the expert on this, you would need to talk to Mohammed, is that the amount that it replaces is insignificant compared to the amount of routing available on the FPGA.
So it replaces some logic blocks, but previous Altera FPGAs, there were like these big RAM blocks in the middle of the FPGA, and I think what they've shown is that it doesn't affect placement and routing that much. So these are even smaller blocks in relatively larger FPGA. So some of the experiments we ran as well doesn't really affect frequency, like critical path delay or something from designs.
So the buffering that you have through there, I mean, what's, if you have really big packets going on, I think the pizza guys call it.
Sure.
See, but pizza.
That's priority. Priority.
Sure.
Yep.
So I jotted down 3R with a question mark. I think that was in reference to the first presentation. And yeah, was that like? I think what I was wondering was whether that was deterministic, like 3R is 3R was the amount of buffering you built at each node. Is that correct? Or am I missing
No,
something?
sorry, I may have been unclear about that. So you're talking about this, right?
Yeah, that's the 3R.
So R here is. Let's go through. So R in that figure was actually the bandwidth injected up each port in the switch. So if you remember here, first see that each transceiver is connected to its own router, so you can consider a router as a injection point for the switch. And so here, R is the injection bandwidth of one port. So for a 10G switch, that would be 10 gigabits per second. And the 3R here is, so under this traffic scenario where you have the red switch is communicating, the blue router is communicating, the green router is communicating. The traffic running through the link there would be loaded 3 times. So it would need to be able to support 3 times the injection bandwidth of a single port.
Okay, but that was only for that specific scenario where you've got the red, green,
Right.
red.
So if you work through it analytically, that crossbar that is the worst case traffic situation that crossbar needs to handle. So there are other situations where a link may be loaded more. Let's say if you have all of them sending to one, but that scenario is considered a scenario of contention where buffering takes care of that. So when you have multiple inputs sending to a single output.
Now, is that specific to this? You've got 16 nodes here. So does 3R change though as I go to a larger?
Absolutely. Absolutely.
So in the packet processor, how do you determine how to route the packet in the NoC? So like, does every processor chooses which destination, and then it just communicates to the router of the NoC which destination should this packet go to?
Right. So the packets that are used, the packets that are set through the NoC contain control information within its flits, and one of those control informations is the destination router. And the routers within the NoC use deterministic XY routing in order to send a packet to its destination.
Yeah, but you mean so like when you get the packet, every packet processor will determine which processor should it go in the next stage, right?
Oh, right. So you're talking about the packet processor. So
yeah.
The first step is determine what's the protocol in the next stage. And then based on that protocol, it has its own little table that determines this protocol is connected to this router, so send to this router.
Okay, so when you partially reconfigure a new
you need to update the tables.
Of the whole, you need to update the tables of every...
Of anyone sending to that protocol. But those are tables, so they don't need to be actually reconfigured. You can simply write to memory in order to update that. Anyway.
Right now we have seen hard NoC and soft NoC.
Mm-hmm.
Hard NoC does give you a lot of benefit, speed and area. However, have you considered something that's mixed, where some of the component NoC is hardened, but some of them is left as soft? In that case, you might benefit from more application-specific NoC design. I'm thinking that if I have a hard NoC, it may not always work well for different kind of applications.
Mm-hmm.
However, some of the components that takes the most area or delay might be hardened, and I can still have some flexibility.
Sure. So some of Mohammed's prior work proposed a mixed NoC, which embedded the routers but did not connect them using any hard links. So you could configure the connections between the routers however you wanted, and that's one way to add flexibility. In his assessments, what he found was a lot of the area of the NoC goes to its buffers. So hardening the buffers was necessary in order to gain some form of efficiency. So it is possible to optionally harden some, but that's something that needs to be studied, right? If we find that enough applications can benefit from this embedded NoC that's hardened everything, that achieves the most efficiencies, so why not harden it here? If you find, on the other hand, that applications could make better use of a different type of NoC that has, let's say, different connections, but the same hardened routers, potentially that could motivate a mixed NoC. So it's all about applications.
I'll ask a question on behalf of Altera.
Sure.
So they've got Stratix 10, it's got registered routing.
Yeah.
Does it change the equation?
Well, we still have to see how well register routing works. We know what the marketing team says.
You're part of the engineering team here too.
We have some of the engineering team. But definitely, register routing does change the equation. The amount of efficiency changes, right? If designs do scale according to what Altera says, I believe they're saying that it's an increase in performance of 2x, that drastically changes the efficiency numbers that we've been showing. However, our designs will still be more efficient because our designs have been more than 2x faster than the actual route. So it's all a matter of if we took these applications and built them out of a registered routing FPGA, what type of results do we get? How do they compare to a hard NoC? Does this still motivate the inclusion of a hard NoC?
That makes sense. One other comment I'd make is the 2x performance improvement that Altera is stating for Stratix 10 includes 2 process advantages. So it's not all registered routing.
It does include process advantages, so it's not quite, you're right.
Would not get 2x faster because it would only get 2 process nodes, but it's going to run at more than 1.2 gigahertz in 14 nanometer FinFETs.
Right.
But that would improve time enclosure, but it wouldn't improve the interconnect efficiency, like crossbars or other things. And also the design effort to create your own interconnect. The idea is to use the NoC to move the data around without you having to design your custom interconnect. So to improve one thing, but from the others.
Playing devil's advocate, just to be clear. I wasn't trying. It was like the advisor comes and basically questions the last pieces of the last day.
Paul, did you
do you have any comments on Stratix 10? We have one of the architects of Stratix 10 here, so.
I mean, some of your savings is coming from areas. I mean, even though Stratix 10 is massively faster, the area savings are still looking
Well, one comment to make is if you're running faster, generally you do save area because your data paths are not as long. So it's possible that some area savings does arrive from having a faster interconnect.
Yeah, but your area savings really come from bundling up that hard knock, right?
Sure.
Well, as soon as you're in the FPGA fabric, you go wide again, but the strongest time will let you stay narrow once you're in the FPGA fabric.
Yep.
So it just reduces the amount of conversion you got.
Yep.
Paul?
Yeah, so a quick question about buffering, like what size of packets, and were you processing, what rate were they running?
Right. Well, in terms of size of packets, we simulated 512 byte packets, which is about the middle in terms of range of packet sizes that Ethernet supports. And the reason we did that, I believe, it was when we were comparing to prior work. Prior work used 512 byte packets. For example, in Dai and Zhu's work, their latency curve was measured by simulating 512 byte packets. So in order to provide a fair comparison, we did the same thing.
Because I vaguely remember there's something called jumbo packets, if they're allowed in the network that you're using, they're like 16 K or something. Big,
right.
A byte overwhelming, right?
They would fill up the buffers and create more contention. If they happen a lot, they'll definitely create a lot of contention. But I would argue the same would happen at any switch.
Sure. Yeah.
If you want to support larger packets, you simply need to increase your buffer size.
Yeah. Presumably they don't have enough.
There's one thing you can do that I know is in your future work that you're going to do the next week before you graduate, is for really deep but unusually used buffers like that, you can dump to DDR, right? And because that's going to start overwhelming.
Yep.
You just have open contention with those kind of things, right? If you have a couple of huge packets like that trying to make it through. I'm putting words in your mouth, but I think the NoC is quite useful as well for connecting to DDR, so it provides a useful way to dump to DDR when you need to as well.
So we actually tried that in some of our designs for the packet processor. Actually wrote RTL and everything in order to take packets that arrive and dump the packet payload, which doesn't need to go through the processing phase of the packet processor, bring it to DDR and only process the packet header. And this alleviates contention with the NoC since you're only dealing with a header, not the giant payload that comes behind it. Now, we don't have results for that mainly because the applications that we looked at don't actually benefit from this dumping. But if you looked at more complicated processing that requires, let's say, larger packets or more switching between modules, that could have some benefit. And the NoC is actually quite good at interfacing with DDR. That's one of the benefits that have been shown in our prior work.
Okay, great. So the pizza has arrived, so thank the speaker.